In the late 1800s, when it was time to put electricity in all over America, build the first power grids, there was a fairly vicious fight between two of history's greatest inventors. General Electric's Thomas Edison and Westinghouse Electric's Nikola Tesla. And they were competing over whether they should use alternating current, which Westinghouse and Tesla favored, or direct current, which Edison favored. It was kind of a vicious fight, and it led to, among other things, the invention of the electric chair, which Edison invented to try to show how dangerous AC was and try to scare people from using it. But in the end, AC won, and Tesla and Westinghouse were victorious. And this video is going to try to explain why. It's because of a device called the transformer. This alarm clock will show us why a transformer is useful. I bought it from the UK, where they use 220 to 240 volts for their electric supply, and I'm going to attempt to plug it in the United States, where we use 110 to 120. Obviously that wouldn't work directly, and that's why the plug is designed to not fit into one of our outlets. But with the transformer, I can actually change the voltage. So let's see how that works. According to this transformer, if you input 110 volts AC, it's going to output 220. So the first problem is getting these pins to fit in an American outlet, and you just use a simple adapter for that. But we still don't want to plug that in even though it would fit, because it would be the wrong voltage. So we'll take our transformer, we'll plug our clock into that, and then we'll take the whole deal and plug it into US Power. As you can see, it works. Radio actually works too. So we were able to get electricity with the changed voltage. So a transformer let us switch from one voltage to another. So in this video, I want to talk about what a transformer is. I want to look at some equations on how we use the transformer. And then I want to talk about what the advantage of changing voltages is in wiring an electrical grid. At its most basic, a transformer consists of a metal rod, in this case iron, a coil of wire that comes in, and is hooked up to an alternating source. And then another coil of wire that's entirely insulated from it, but is wrapped around that same metal object. It turns out that even though there's no electrical connection between the two, you can actually make a light bulb light, or you can power a circuit using this arrangement. I'd like to show you this. So I'm going to use the DC lab power supply to show how a transformer works, and one of the issues with using the DC that Edison wanted to use. So I've got 5 volts on the lab power supply. I've got this old chair with steel legs. And to this coil of wire, I basically have the positive from the lab power supply hooked up, and I have the coil also hooked up to a knife switch so that we can turn off the electricity and turn it back on. There's plastic inside here. There's no electrical connection other than to the power supply and the switch. So we'll just slide that on. I got this other coil, and the only thing it's hooked up to is the voltmeter. So we'll slide that on. There's no electrical connection between these two coils. But I want you to see what happens when I turn the electricity in this coil on, we're going to see that it produces a measurable voltage in this coil, even though they're not connected. So here we go. Electricity. So you saw when I first turned it on, there was voltage. And when I turned it off, there's voltage again. But it stops pretty quickly. So on, there's some voltage, it goes away. Off, there's some voltage, it goes away.
You probably recognize coils like this as being the same ones we used back when we studied magnetism. And we saw that in order to produce voltage in one of these coils, we had to move a magnet in and out. It couldn't just stand still, it had to be constantly changing.
So right now, with no current inside the primary coil, there's no magnetic field inside the secondary coil, so we see nothing. If I change the magnetic field to non-zero by turning on the primary, we briefly, during the time of change, see electricity in the secondary. But then it goes back to zero because it's not changing anymore. It's like you've shoved the magnet in and haven't pulled it out yet. Going back to non-zero briefly gives us electricity again, but then it goes away. So you'd have to keep turning this on and off. We have another way of continuously varying current, though, and that's alternating current. Let's look at an alternating current power supply. The way it works is we have a coil of wire, and this will be my first coil of wire right here. And it's hooked up to some alternating current power supply. It has to be AC because to create changing magnetic fields, we need to have constantly changing currents. So I've got this hooked up to my AC power supply. It's wired to the yellow terminals. And then I'm going to slip this over this steel chair leg. And what that's going to do when I turn on the power is it's going to create a changing magnetic field in the coil of wire, which the chair leg is going to carry along it. Now I've got another coil of wire over here, and it's not hooked up to anything other than this voltmeter here. So what's going to happen when I turn this on, the coil to the right is going to have a changing current, creating a changing magnetic field. A changing magnetic field is going to extend into the coil on the left, which is then going to create a changing current. And the voltmeter should pick up that there's now an alternating current voltage. So I'm just going to go ahead and switch on. And we can see that we do indeed create a voltage in the second coil. Now this is not a great design for a transformer. It's not particularly safe either, so I'm going to turn it off real quick. But it shows that we can use magnetic fields as a linkage between two coils of wire, and that's the basis for a transformer.
In order to continuously make electricity in this coil, we have to be continuously changing the magnetic field inside it, which means we need to be continually changing the current in this coil. That's why alternating current is required.
So there's other better designs for a transformer than this that capture more of the magnetic flux coming out of the input, which we call the primary, and direct it into the output, which we call the secondary. But we can use this model for now. There's a few big ideas about transformers that we have to mention. The first is they're a trade-off between voltage and current. So you probably remember voltage when I was throwing the ping pong balls at this board. Voltage is the energy a charge carries. So when I was throwing those ping pong balls, it represented how hard each ball was hitting the board. Current represents how many balls you get per second, or how many charges you get per second. They're not really what matters when it comes to electricity. What's really important is power. How much energy are you delivering per second? And a transformer doesn't create energy. So the key thing about it is that the power going in has to be equal to the power going out. Now we know the equation for power is current times voltage. So that means the current in times the voltage in has to be the current out times the voltage out. So what good is this? Well, a transformer allows you to play around with one of these variables and have an effect on another variable to make this equation still stay true. I have to show you what I mean. Take my British clock. We had an input voltage that's relatively small. And we had an output voltage that was relatively large. What compensated for this? Well, you can still have the same power on both sides if I put in a large current and took out a small current. So that's what a transformer does. It essentially allows us to switch between a small voltage with a large current and a large voltage with a small current. It does this by putting coils of wire with different numbers of turns on each side of the transformer. The best description of this I've seen is in Paul Hewitt's Conceptual Physics, so I'd refer you there if you've got further questions. But the bottom line is if these two coils, the primary input coil and the secondary output coil, had the same number of turns, and all the magnetic flux coming out of the primary ended up in the secondary, we'd expect the input and output voltages to be the same. If you have more loops of wire, we expect you to get more voltage in that coil. So by varying how many coils you have on one side versus the other, you can determine how many times bigger or smaller the transformer makes the voltage. The equation to do that is voltage in divided by number of turns in equals voltage out divided by number of turns out. So I have a set of coils from Pasco physics that we can use to check whether this relationship is true.
Let's start with our British alarm clock. It's in the United States where it's getting 110 to 120 volts. It needs twice as much, 220 to 240. What kind of transformer would we need to accomplish this? So let's try to use the equation to solve for what the alarm clock needs in the United States. We know our input voltage is 120. And what I'm going to say is that we don't know the number of turns, but we can approximate it as being 1. Because we're not really interested in the actual number of turns of the wire. We're interested in how many times the number of turns are there on each side. So we'll say our input, if we don't know, just has 1. That equals our output. We need it to be 240. And we don't know how many turns that will have, so we'll just say it's over X. I think you guys can easily see what the answer is. In general, if it's harder to see, you're just going to cross multiply and then use algebra to solve. So this would be 120 X equals 240. So of course you divide both sides by 120. And we get X is 2. So that's pretty much all you have to do, and it gives you a prediction of how much voltage you get on the output side of the transformer. This is a set of transformer coils made by Pasco Physics, and what's important about them is that they differ in number of turns by a factor of 2. So the yellow one, which we're going to use as our primary, it has 400, and you can see we have one that has half of that, one that has twice of that, 4 times that, and 8 times that. So we're going to see how this transformer transforms an input voltage of 3. So in all these photos, the primary will be the left side, and it has an input voltage of 3, like this meter shows. So here we have 2 identical coils. They're not connected, so the magnetic flux coming out of this coil is what's causing a voltage in the other coil. Since these are the same coils, we'd expect them to get roughly the same voltage. 3 divided by 400 should be equal to 3 divided by 400. We lose a little bit because the transfer is not 100% efficient here. We still have a primary voltage of 3 here, but we have 800 turns or twice as much over here. So if you solve that transformer equation, you should get twice as much voltage, or 6. You can see we're roughly in that ballpark. Again, there are some losses. This coil has 1600 turns, or 4 times the input, so we expect 4 times the voltage. That would be 12. Again, we're pretty close. We are losing some. Here's what 8 times as many turns looks like. We expect 24. Transformers also can be used to lower voltages. So this blue coil has half as many turns as our input coil. So we'd expect our 3 volts to drop to 1.5. It drops to about 1. This is important if you have an American device and you want to take it overseas. You have to be able to lower the voltage so it would work with our device. There's one other thing worth mentioning about alternating current and transformers. These 2 graphs of voltage versus time are supposed to show Europe, the taller curve, and the United States, the shorter curve. Transformers can change one voltage into the other. Remember, with alternating current, the voltage changes continuously. That's why a sine wave is a good model for it. But if you notice, there's 2 differences. In the United States, we go through a complete cycle and get back to our starting voltage 60 times every second. In Europe, this happens 50 times every second. So there's different frequencies, they call this. The transformer can change voltage, but it cannot change frequency. And that has a pretty profound impact on the clocks. I got this idea from a friend of mine who moved to England after college and had some trouble with an alarm clock. Alarm clocks keep time by counting how many times the line voltage changes each second. In the United States, a clock expects that to happen 60 times, and every 60 times it just says 1 second has passed. That means it's made differently than Europe, which counts up to 50. So a clock that's been brought to the wrong country is going to keep time wrong, but in a very predictable way. I have the British clock and an American clock synchronized at the beginning of my first hour physics class in 2016. So I plan to run the clocks until 9 a.m. that day, which is 34 minutes. In America, where they actually were, we expect 60 seconds in a minute and 60 waves in 1 second. So that means 122,400 waves are going to hit the clock. The clock thinks it's in England, though, so it only expected 50 waves a second. So if you do those conversions backwards, but say 50 waves a second, the 34 minutes to the clock will appear to be 40.8 minutes. So the clock should think it's 9:06 a.m. So this difference in frequency should cause a very predictable difference in time. Let's see if we were right. And we were. Exactly what predicted, 9:06 a.m. So this shows you what a transformer can and can't do. This caused my friend some considerable trouble in England. The clock wasn't keeping time right.
So I said at the beginning of this lesson that there had been a big fight between Tesla and Edison over how we were going to wire the country. And Tesla won because the ability to change voltages turns out to be super important when it comes to delivering electricity. And the reason for it is that current is the enemy of efficiency. You've learned already that it's dangerous to have too high a current because it causes the wires in your home to heat up. If they heat up enough, they could cause a fire. The other problem with heating up wires is that that's energy that's being wasted. You're not plugging in a coffee pot to heat the air up. You're plugging in a coffee pot to make coffee. So anything that doesn't go into that task is wasted. The two equations we know for electricity can explain why current wastes energy. We know that P is IV, and we know that V is IR. If we sub in, we can see that P is IR, or that P equals I squared R. So for anything that has resistance, including a wire which has some resistance, the more current you have, the more power is going to be wasted as heat. Voltage isn't in this equation. So the obvious solution is, why don't we transmit electricity with really high voltages? And we do. The problem with that is, you can't put 125,000 volts into somebody's house. 120 volts is dangerous enough. People still get shocked with that sometimes. And a lot of those people survive. But if you had 125,000 volts in the house and somebody accidentally touched both sides of it, the amount of current produced would kill them instantly. You can't have that in somebody's house. So to get around this problem of current being a waste of energy, we can use high voltages to transmit electricity, and then we can use transformers to change those high voltages into low voltages that are safer. So in the path the electricity takes to get to your house, it's made at the power plant with a certain voltage. A transformer then brings it up to extremely high voltage, hundreds of thousands of volts, and it's carried long distances on high tension power lines. Then when it gets to a city, it goes down into a substation, and it's converted to a relatively low voltage, a couple thousand volts. Then when it gets to your neighborhood, it's converted into 240 volts, which goes into your house and is split into 120. So these transformers allow us to have high voltages where people aren't accidentally going to touch it. That means low currents, and therefore not wasted power. We then can convert it into low voltages in our houses. That of course means the current's going to go up, but it's safer to use it, and we get our electricity without the huge hazard. That was only possible with AC current in the late 1800s, early 1900s, and that's why we chose AC for our distribution network. For more information on this, I highly recommend reading the description of Paul Hewitt's conceptual physics.